Okay, so this problem confused a lot of people. What's happening is there's this ramp that we don't know how long it goes on, so we just assume it goes on forever. We're not given the incline angle of the ramp. We're just given that we're given a clue though. This 10 kilogram block for every 5 meters up the incline, the height of the incline is raised by 3 meters. So if you go another 5, it would be here, and then the height would be 6 meters, and then so on and so on, so on and so forth. This allows us to get the angle though. You just think about this triangle with the hypotenuse of 5, an opposite side of 3. The sine of the angle has to be opposite over hypotenuse. Therefore, theta is inverse sine 3 over 5. 3 divided by 5, sine inverse. I get theta is 36.87 degrees. How much work does gravity do if you push the box 7 meters along the ramp? The easiest way to do this is to just find out how far up the vertical displacement 7 meters corresponds to. 7 meters along the ramp. And so just imagine the triangle with 7 here, and then 36.87 degrees here. What is this height? Well, h over 7 still has to be sine of 36.87. Sine of 36.87 was 3 over 5. So maybe it's probably more accurate if I use 3 over 5. That means h is 7 times 3 over 5. So that's 21 divided by 5, 4.2 meters. And so gravity will have done, work by gravity will have done negative mgh, negative 10 times 9.8 times 4.2, 8 times 10, so negative 400.6 joules. Or what we could do, so that's one way, or what we could do is find the work, or sorry, find the vector for the gravitational force. Okay, let me, in a different color, let me just draw right on the figure. Okay, gravity is pulling on the box straight down, but we're interested in a rotated coordinate system. Which I'll call the direction parallel to the incline, positive x prime, and then the direction perpendicular to the incline, y prime. W in this coordinate system has two components. Component this way, and a component this way. The angle here is theta, just like the angle here. And the x component, the x prime component of w is going to be the magnitude of w. I've got a negative sign because it points backwards. Sine theta I hat prime. So prime means rotated coordinate system. And then a negative w cosine theta j hat prime. The displacement is going to be 7 meters along the x prime direction, so that's just 7 I hat prime. And then now, the work due to gravity, I'll use these two vectors because that's just w dot s, negative w sine theta I hat prime minus w cosine theta j hat prime dotted into 7 I hat prime. Only these two terms dotted together survive. This term and this term has a j hat dot I hat, which is 0. So negative w is just mg times 7 sine theta I hat prime dot I hat prime. That's just 1. So this is negative 10 9.8 7 sine of 36.87, or I could have just used 3/5 like I did up here. I'll go ahead and use 36.87. 36.87 sine times 7 times 9.8 times 10, negative 411.6 joules. So, I don't know. Whichever way makes more sense to you. Okay, what is the normal force between it and the ramp? I guess it means the block and the ramp. So I'll draw the free body diagram again, or the force diagram again. Here's the normal force. Here's the gravitational force, the block's weight. And the applied force F. So the incline is something like in that direction. Then the perpendicular direction of the incline is like this. If there was no applied force here, then the normal force component and the weight would have to balance. But this force is actually pushing the block into the incline a little bit harder than it otherwise would have. So I expect the normal force to be bigger than the usual, what do we usually see? mg, this is theta, usually mg cosine theta. Like we typically see that the normal force is equal to mg cosine theta. But in this case, since we have an applied force that's just pushing the block into that incline a little bit harder, I expect this to be the case. So we'll see if that's true. If it's not true, then I probably did something wrong. So basically, we have to do a lot of projecting of the vectors onto this x prime, y prime coordinate system. So n, we don't need to. N is already done. N vector is the magnitude of n, whatever it is, the thing we're looking for, but it's all in the j prime direction. F is a little bit more complicated, so we've got this component of f, which is f cosine theta. That's the x direction. And then this component, f sine theta, negative f sine theta, because it's pointing down. And the j prime direction. And then w, well, I just did w, that's negative, I'll just go ahead and write mg sine theta, theta I hat prime minus mg cosine theta j hat prime from up here. I know that when I add all the forces together, I get the total force. That's going to be equal to ma, and that will be ma in the max I prime hat plus ma in the y prime direction j prime hat. And I need this component to be 0 because the block cannot accelerate in that direction perpendicular to the incline. That would be weird. So the y prime component of f total should be 0. So that's just a note. So let's add it up. F total equals, let's do the x components first, or the I hat components. F cosine theta from up here minus mg sine theta, that's all in the x direction, plus n minus f sine theta minus mg cosine theta j hat. And indeed, so that needs to be 0. That means n minus f sine theta minus mg cosine theta is 0. Solving for n, we have n is equal to f sine theta plus mg cosine theta. Right? In a lot of the problems we've seen, n was just equal to mg cosine theta. But now in this problem, the presence of that applied force adds on a little bit extra to the normal force. And so the normal force in this problem is greater than just mg cosine theta, which is what we saw. Get rid of those. So this is the expression. And the numerical value, f was what? F was 400. 400 sine of 36.87 plus 10 times 9.8 times cosine of 36.87. Not really consistent with my parentheses. All right. 36.87 sine times 400 equals plus 10 times 9.8 times 36.87 cosine equals 318.4 and is equal to 318 joules, or newtons.